Thank you so much. I'm really excited to be visiting SFU and talking about some topics that are very close to my heart. I will be talking about feature engineering and domain expertise exemplified in two case studies, one on text where I'm a domain expert and another in images where I'm not. And then I will use that to drive some discussion. So, particular, I will introduce a little bit about my idea about the machine learning and feature engineering cycles, particularly how I see them deeply tied to a human-in-the-loop approach for machine learning based on exploratory data analysis and error analysis. And the case studies are built on a data set that I have put together for the book that you can download from the website of the book. It's based on open data. And then we'll have this discussion. So throughout the talk, I have added these little quotes and topics for discussion to try to get you back from your portable devices that are always a big competitor when you give talks. So I gave a talk on this topic a few months ago in Panama City to the IEEE Computational Intelligence Student Society on, and there was this mechanical engineer in the audience, and he says, what do you mean you will do turbine failure prediction without being a turbine engineer? Yes, and in a sense, in data science, we many times end up doing these type of things, and I really like this quote because it highlights our arrogance of trying to do this type of things. And what I explained to him is, well, imagine you have these turbines in a power generation company, and you just purchase them from from a company. So the company that sold you the turbine has the turbine engineers. And you have data about when your actual turbines that you have installed fail. So from there, you may be able to predict these failures, and without having to have a person in staff that is an engineer in turbines. So, okay, that sounds like a reasonable use case. But still, something that I'm trying to argue throughout this talk is that even if you don't have the turbine engineering staff, you may want to reach out to them to help you. And if you do that, you will have a more informed model, and you will have better quality predictions. So when we talk about machine learning and AI, there is always this question about, okay, are these things helping build intelligent machines, things that will mimic human behavior? And I want to say this topic is quite important for feature engineering, because feature engineering is quite far away from building intelligent machines. Yes, so what we are trying to do here is just solving problems using computers, and I personally see machine learning as evolution of programming. Therefore, we have a collaboration between humans and machines. Feature engineering, therefore, is very laborious, and it helps to improve the performance. And it's a method for injecting human knowledge into the machine learning systems. These days, there has been quite a move towards deep learning in the field, and clearly deep learning is a step towards building artificial generalized intelligence. Well, feature engineering is not. I would expect that in a decade or so, statistical machine learning will no longer be considered AI. It will be considered a way of doing, say, probabilistic programming. And that's okay, and feature engineering will be a part of that type of effort. From this talk, the main takeaways is that, well, many tasks will involve this type of hybrid machine work, very similar to programming, and that domain expertise can help the data science process. And so if you later on end up being practitioners in the field, keep in mind that if you don't have domain expertise, you may be better off seeking out to that expertise. And this is something that has come from you. The persons hiring you may not want to pay for external domain expertise, or they may not think you need it. Yes, they may be happily thinking you don't need a turbine engineer for doing this failure prediction. And for the people willing to continue doing research, the question about how you quantify domain expertise, how you quantify the impact, is a very difficult problem get it exact enough to do research upon, but that I think shouldn't stop us from trying to do real research. What I'm showing here is more of a case study, so it's not quantifiable things, but definitely it's something to look into. So I assume throughout this talk that when I talk about machine learning, I'm talking about supervised learning, particularly classifiers, and the input to the machine learning system will be this set of instances that have features, but the input to the problem is this raw data. And the feature engineering process includes transforming this raw data into these features. And together with the instance, we have a target class or a target value. That is what we are trying to do, the classifier or regressor. So we are all familiar with the machine learning cycle where we do a train, test, split, build a model, and evaluate it. For the purposes of feature engineering and to think about this process more from a human-in-the-loop perspective, we want to start from an exploratory data analysis. We take that raw data and get data insights. We start understanding how this data behaves and decide which model are we going to train. This is a step that is seldom discussed, but is quite important. And then we also decide which metrics are we going to evaluate the models. From there, we featureize the raw data to obtain feature vectors, and those are the feature vectors we do the train, test, split, and we build the model, and then we evaluate the model. So throughout the day, I'm very happy to see that there is people here working quite a bit on exploratory data analysis. To me, it's a key component of machine learning. And the intention is, therefore, in exploratory data analysis, to summarize the characteristics of the data sets being used, normally through visual means, and to help formulate hypotheses about the data. As I was mentioning, in the machine learning case, that helps pick up the model and some idea about initial featureization. So with this concept, we can arrive to the definition of feature engineering for the purpose of this talk. Is a process for representing a problem to make it amenable for learning techniques. And this process involves initial discovery of features and their stepwise improvement. It's based on domain knowledge and the observed performance of the ML over specific training data. When I met with the students earlier, they were saying, well, feature engineering is used to refer to a number of different topics. What does it mean to you? Well, to me, it means all those topics. You know, here you have dimensionality reduction, you have the analysis of the data, you have the piecewise improvement, but foremost is a process. You follow a feature engineering process, and the main result of that process is better understanding of the problem and the data on behalf of the person doing the process. From my perspective, what we are doing on feature engineering is we are trading data with human time. Similar to in computer science when we trade time and space. Yeah, so we can speed things up by using a cache that uses more RAM. We can use less RAM and doing multiple passes on the data, which takes more time. So in this case, if we have very large amounts of data, we can go do without doing any feature engineering, and that's precisely the premise of deep learning. We can synthesize better representations using neural network layers. Instead, we can use human knowledge to help using the problems with computer. And again, this doesn't help building autonomous intelligence systems, but in many situations, you don't have enough data to do feature representations. So what are good features? Good features are informative. Yes, the feature describes something that makes sense to a human. They're useful. They are defined to as many instances as possible, and they are discriminant. They define instances into different values for the target class. So with this idea of how machine learning works and what makes good features, then we can arrive to the proposed cycle for feature engineering. This cycle does an iteration on the ML cycle we saw on the earlier slide, and it starts by splitting the raw data. So we have the initial data we have, and we split it to have a final test set. When you are doing feature engineering, there is a very good chance that you will overfit not the model, but your features. You will find some structure on your features that doesn't really generalize beyond that. For example, you may be using raw data that is only collected because you didn't do a good split here, that is only collected in the summer, and then your final evaluation includes raw data from the winter, and the features you found are really good for summer data, but not for winter data. As such, after you finish your cycle, you should evaluate the trained model on this unseen raw data. So in each cycle of the machine learning, what you are doing is doing error analysis. Yes, and here is also a part where I want to highlight having a human in the loop. It's very common these days to just do error analysis by looking at aggregate metrics. How many times you get this right, how many times you get this wrong. That's a good start, but that doesn't really help you do quality feature engineering. For me, error analysis for feature engineering is about finding individual cases of errors and come up with a clear understanding about why the system failed for those particular errors. For that, you can use a contingency table, and you most probably will need to have your whole machine learning system instrumented so you can go back about the type of decisions that led to that mistake. From there, you can build a hypothesis that says, well, I believe this is failing because I don't have enough training cases for this, or this feature is taken in isolation when it should be taken into a particular context. And then you try to see whether that hypothesis actually covers a lot of error cases. Because you don't want to over-optimize, you don't want to over-engineer. You want to make improvements that will pay off. And one of the type of things you can do for feature engineering based on the error analysis is this technique called a feature drill down, where you drop poorly performing features. Simpler models have less parameters, and that allows them to be more informed over the same amount of data, and you expand good ones. You take features that look good and you make variations over them and try to combine them. You can also go back to the raw data and do more exploratory than analysis to hypothesize new features. So this is a little bit of an introduction of feature engineering, and I'm going to talk a little bit now briefly about the book. So the book is coming, yesterday I received the last chapters for the copy editing, so it's coming, I think it's in February or March. The focus is really helping practitioners. So it's people who are already familiar with machine learning algorithms, have already trained models, and it's also helping them approach new domains. So let's say you are doing text or images. There are whole books about how to do feature engineering in those domains. But if you are working in a little more exotic domains, then you are kind of on your own. So one way that is understood that you can generalize this type of knowledge is to understand clearly how people do feature engineering in these other domains to help you bridge that gap. It's material that is seldom presented in a book format. I reach out to blog postings besides research papers and other type of material, and it includes 5 case studies with 10,000 lines of Python code available open source at the website. And so I've been reading this book called Computer Power and Human Reason. I don't know if you ever heard about that book. It's a book from 1975, written by Joseph Weizenbaum. Joseph Weizenbaum is famous for having written ELIZA, this, you can call me the first chatbot. So later in life, very close to his death, he completely disowned that work. He really didn't like it. And he wrote this whole book about computers and ethics. And it's a fascinating reading, and the Vancouver Public Library actually owns a copy of this book from 1975. One of the things he discussed in chapter 4, called it the compulsive programmer, is the fact that science is like that joke of the drunk person that is searching for his keys next to a lamppost, even though he lost them far away because the lamppost is better light. Yes, so he can search better. So what it says is, in science, we search for questions for which we have methods and data, but we don't necessarily search for the questions we need answers. And that's a little bit what I'm trying to get at. Well, feature engineering is needed, and we need more research on it. And domain expertise is needed, and we need better research on it. But these are topics that are very hard to do research. And something I'm very happy from meeting you all earlier in the day is to see that you are doing research on data cleaning and data preparation, some of the topics that are most needed and very, very hard to do any work on. Okay, so this is my presentation slide. I like to have them later in the talk. But the thing I was to mention is that I also do a lot of reviewing. So if you complain about reviewers, are people like me. And okay, so I spent 9 months of my life writing this book and even more time researching it. Why? The first one is when I was in the Jeopardy project, I worked on the machine learning component at the end of the project. And in the Jeopardy project, we have this ensemble system that was running in these thousands of cores and producing all this information that came to this final component that has the answer merging and scoring. That one, I developed a domain-specific language for doing feature engineering, and the whole system ended up being this little monster using normalization, a Bayes system, a transfer learning, and answer merging, using all logistic regressions at this stage, and reducing the number of answer candidates. And what I learned while doing that was that we get a lot of mileage from feature engineering, even more so than improving the original subcomponents. And after we did that, I went to teaching, and I taught a course on machine learning over large data sets with Mahout and Hadoop. Spark was a little too early at that time. If you want to improve your Spanish, I have all the lectures available on YouTube. And in one of the lectures, I wanted to cover feature engineering. Of course, I thought it was a very valuable topic. And what I found out that there was no material for teaching a lecture on feature engineering. So later on, I also realized when I was consulting, I found that many practitioners were only focusing on model selection. They were performing very little EDA and doing error analysis on aggregate indicators. So they will basically take data, feed it into a model, feed it to another model, and so forth, so on. And to me, they were missing out a lot of improvements of their model because they never stopped to consider better their features. So when I took a personal sabbatical in 2016, I revisited this idea of writing a textbook. I found that Alice Janks had just published a book on O'Reilly on feature engineering, and I still thought I have a different view on the problem and looked for some publishers. So I took, and you can call a top-down structure, and I looked to flesh it out. So my textbook, compared to other ones, is more like a big toolbox of different techniques based on an organization on the data. And I organize existing papers, some papers even from the 90s that there is some pretty good work, for example, on discretization in the 90s that is quite forgotten by now. Also, most textbooks talk a little bit of feature engineering, so I try to fish out that. And then non-traditional sources like videos, Quora, Stack Overflow, and class notes. That's why the book ended up having like 330 citations, which for a 200 pages book is quite packed. So why do I care about the toolbox? So Stephen King, the horror writer, has a book about writing, called it very imaginatively on writing. And there it says that you want to construct your own toolbox. Why? Because then when you look at the hard job, instead of getting discouraged, you will just get the correct tool and get to work. So he sees the personal toolbox you have for your trade as a source of reassurance. Yes, the anecdote he was telling us about his uncle carrying this big toolbox with him just for a screwdriver. So why do you take the whole toolbox? Well, it's because that helped me not to get discouraged if I am using the screwdriver and then something breaks and I need a hammer. Yes, I know I have a hammer there, so I don't mind if things break. So I do find that knowing all these techniques of feature engineering, even if you don't foresee that you're going to need them, give you a toolbox that later on makes a difference when you're working on the field. So the book has two parts. The first part starts with this process description I just mentioned, and I talk about how to combine features to do normalization, discretization, outliers, how to expand features with computable features, imputation, and kernels. I have a chapter on reducing the feature space with feature selection, dimensionality reduction, and embeddings. And then I cover feature learning, AutoML briefly in the last chapter. The most interesting part in terms of this is unusual is that the other half is just case studies where I spend a week or 2 weeks per domain and I documented 10 to 20 small programs in a Jupyter notebook to do several cycles of feature engineering over real data. We're talking, this one is about 300 megabytes compressed. This one is 5 gigabytes compressed. So this is a data set that is interesting enough to do real machine learning, and it's all on an open license because it comes from Wikipedia or from NASA. So it can be redistributed and use it for your own learning. And the source code for all these Jupyter notebooks is distributed on an MIT license, and it's available on the website. I have this slide here about AutoML from the perspective that I thought that this would be quite interesting for your group, and clearly, well, I met with people who are working on AutoML. At the conclusions of the book in the introduction, what I said is, well, if you have enough data to do feature engineering, to do deep learning, just do deep learning, don't use feature engineering. And if AutoML produces you good results, then use AutoML, don't feature engineering. I see feature engineering kind of similar to going to court and waiting that the judge give you a decision on your case. If you can avoid it, you are better off. And why is that? It's because feature engineering tends to fail. You try things with the data, modifications, with some hopes, but then it many times doesn't work. And that's captured also in the case study. Another topic that I'm quite interested in is having a domain-specific language for feature engineering, and this is something I will be interested in collaborating. I talked earlier with some of you about this work by Ray and also Anderson and Caffarella on expanding SQL with feature engineering components. So you consider that you're executing a query that produces the training data from which you train the model. And that way of thinking, I think, is very rich. And in this paper from 2016, they even compute the deltas between the original query and the feature engineering step, and then retrain the model only for the changes. And I really would like to see more work on that. And to me, the storage engine is the right place to perform feature engineering. Yes, featureization is inherently a data manipulation, and of course the database community is the one who knows about those things. So to me, a SQL extension that allows you to do things like target rate encoding or some of the most complicated parts of feature engineering will be quite exciting. Okay, so now for domain expertise. So we have these two viewpoints. One is that you should be able to do all the work as machine learning without knowing anything about the domain. And I met plenty of people who tell me, oh, I don't know anything about language. For me, words are just a feature like anything else. And, and well, good luck to you. And then, so the idea here is that careful data analysis, just by looking at the data, you should be able to understand which assumptions are bad and find high-performing models. There is a Kaggle champion that has a YouTube video called Data Agnosticism, and he insists that responsible data analysis and quick iterations produce high-performing predictive models. And I believe he's right. In a sense, when you have too much domain expertise, sometimes you become concerned about certain things, and you move in a way more reluctantly, and sometimes simple ideas work better, and having this fresh view on the problem can help. However, there is a bigger problem in the sense of if you believe you don't need any domain expertise, then you will never seek out for it. And our society and our way of thinking and working and teaching is quite into silos, right? So this idea that domain independence make it even worse. So you go to school and they teach you don't need any domain knowledge, and then you go to work and your manager says you don't need any domain knowledge. This organization is doing data science independent, and that's really has its drawbacks. The other aspect is that when you say expertise, I like a quote from a book about patient-doctor communication that says a doctor visit has two experts at work. You have the expert in medicine, that is the doctor, but then you have the expert on the patient's body, that is the patient themselves. Yes, so if you work with a data set long enough, you may actually become an expert on that data. And that level of expertise should not be, it's different from domain expertise, but it's data expertise for that particular data set. And that's quite common actually in long-term data science projects. So what the subject matter experts bring you is know which data features are important. So for feature engineering, that's really useful. I like the quote, like if you want to go fast, go alone, but if you want to go far, you have to go with other people, and if you want to go really fast, you better ask somebody who knows the way. So the main part is avoiding costly mistakes. Yes, if you want to reinvent the wheel, then most probably you will start with square wheels and not really get that far. And as I was mentioning, many of the techniques presented in the case studies didn't work on that particular data. And that was something I wanted to showcase, how much trial and error is involved in feature engineering. Still, the case studies have about 50% success rate, and I found that's too optimistic. I would think it's more like 10 or 20% if you were to do this in practice. This is quite hard if you think about it, how you communicate this without looking like you don't know what you are doing. Yes, if I were to just take all the things that work on the case studies and just make a book on that, it will give the idea that feature engineering is this type of magical thing. You take a magic wand and all your data works well, but that's definitely not the case. And many times when you try some feature improvement and it doesn't work, you learn more about your data set and your problem than if everything magically works well. Dr. Ursula Frankling was a metallurgy professor in University of Toronto, and in 1989 she gave these CBC Massey lectures, The Real World of Technology. And it's a fascinating lecture. You can still listen to them on the CBC website. There she has this quote that says, tools often redefine a problem. So by having a toolbox with feature engineering, you can also think that problem as a representation problem on which you have a saying about what the representation means. And that helps say, well, why to learn a little bit of feature engineering even though you will still use other type of techniques. So as I was mentioning, I have put together for the book this data set, the Wikiset cities data set. And the intention is to exercise different feature engineering techniques. So we have the same problem, predicting the population of a small town or a city. And we have properties coming from tabular data. We have the textual description, the historical population, and satellite imaging. Yeah? So any of these different views of the data should help you predict their population. The base data come from the DBpedia project that extracts a semantic web information from the info boxes on the Wikipedia page. There's little boxes next to the, and so distributed as triples. So you have New York City, the title. So chapter 6 on graph mining is based on this, and these are the various features the other chapters later on use. So when we say text and images, it's text plus this relational data and images plus that relational data. Okay, so now drilling down on the text case study. The intention of showing text is to show a custom feature generation through custom tokenizers, feature selection, feature weighting, enhancing a feature by its context using bigrams and scriptgrams, and domain-specific reduction using embeddings. And one of the key parts here is, because I was profiting from my domain expertise, that allows for richer hypothesis building through error analysis. So what you can see here is, when you look at the behavior at error analysis, years of experience allows you to quickly understand how to improve the system. So I've been working in NLP since '97, and one of the reasons I got into the field is, besides the machine learning and deep learning aspect, I really like linguistics. And I even took a graduate course on syntax for natural languages that was offered at the computer science department in New York. I went to a high school that was a humanities focus. I took 5 years of Latin, 3 years of ancient Greek, French, Italian. I also took English, even though it's not that clear. So I do actually love human language and communication. And for me, NLP is not just a domain to apply machine learning to it. So this is a graphic representation of the notebook for the case study. So it's quite big. Each of these is a screen. And the notebooks are written in a little verbose way because it's intended more as communicating ideas rather than, I mean, it's as far as production code as you can get. And it's also trying to reduce the number of dependencies and to help people get these ideas they want to implement in other languages. Okay, so in the exploratory data analysis, what we look is that bigger cities have longer pages. This makes sense. We take 10 cities at random and see that most of them have the population present but with punctuation. And some punctuation has mistakes, and it's going to be quite ambiguous. You know, this 2000 and this 2004 look pretty complex, and some cases don't. So from there, the first featurization of the text is just don't look at the words and just look at the numbers. Look at how different this is from a traditional natural language processing without doing language analysis it will be. Because numbers in general are discarded when you use machine learning. They are too different. I mean, they are not discarded explicitly. You just have each number is a different word, that you do some dimensionality reduction, they are going to be disappear because they are very rare. Instead, what I do here is from the chapter 6, I have been a discretization that I know makes sense for this domain in only 32 beings. So then I transform all the numbers I see in any of these 32 features, and that actually works quite well. Feel free to ask questions anytime, by the way. The second approach is to do a regular bag of words, consider the words as independent features, and to retain only the top 1,000 words that have higher mutual information. And then if you look at the top 20 tokens, things like capital, major, international appear there, which seems to indicate things are working. And I do then an error analysis on the cities that improve a lot or decrease a lot when we add the text. And the top winners are well-written, long documents for cities that are far from the Western world, therefore have very little property coverage. So here the text is helping us on top of the properties. More interesting is what happened with the ones who lose performance. And what I can see there, and you can see if you look at the code and the results, is that there are not enough of the top 1,000 words. Like the top 1,000 words are missing some clear signals. And what's happening is that there are too many stop words there, words without the meaning. So filtering them and conflating morphological variations, like dropping plurals, helps increase that signal. And from there, I started to add some context to the features by using pairs of words that appear together, what's called bigrams, and then try to even go further by using any pair of words that appear up to a distance of 6, those are called skip bigrams. And the last item is to do some embeddings and dimensionality reduction with TF-IDF. So this is the whole case study, and it did work quite well. Most of these techniques improve over using just the feature vector from relational data. And it was this is for comparison with the next case study that is doing images. So what I wanted to exemplify in processing images was working with sensor data, when you have a large number of low-level pieces of raw data. And in that case, what we are dealing is with these things called nuisance variations. A tiny difference on the acquisition on the sensor means your raw data changes a lot. But that change doesn't really have any semantic for the domain. So how to cope with that is to compute smart aggregates over this raw data and use those smart aggregates as features. Therefore, like normalize the features when you have a high variance. So the interesting thing about this case study is because I built it by studying textbooks on computer vision. I tried traditional computer vision techniques, and I ran into a number of dead ends. And then I consulted with friends of mine who are experts in computer vision, and they explained to me how they would have realized that those were dead ends before, and they would have not even attempted them. So this is the Jupyter notebook, because computer vision has some more nice features, and it was quite longer than the text one. So the first one, the first part of the exploratory data analysis is, these are satellite images of elevation, yeah? So these are different cities, and you can see how the topography of the cities is represented on the histograms. So the first visualization is just take the center of the city and take a 32 by 32 square and take those 1,000 features as a feature vector and just run them through machine learning algorithm. And one way of representing this is as to do error analysis is to do a feature importance per pixel. Yeah, so here this doesn't look like the system has learned anything. every pixel is the same. Then I try a few techniques to improve this, like Gaussian blur, whitening the data, and also try to do an error analysis where I will turn the data a little bit, like shift it a little bit or rotate it a little bit to see whether that changed the prediction of the ML, to see how robust the ML is to these small variations that we know carry no meaning. So the second featurization then is use that technique of automatically producing variations to make the classifier more robust. So each city now has 4 times its representation of the training data with the original image plus 3 random variations. And the variations can be rotation, translation, and compression. And these actually improve over the baseline, and it shows that the system is focusing much more on the center of the city, which seems a positive result. The third one is to use histograms, because we know that histograms make the system robust to rotations and translations, and this was a little better, but in reality none of these systems was better than just using the data alone with no images. The fourth featurization was using local feature detectors in the form of corner detectors. And again, this is the idea, is to provide better context to similar features. Corners are placed in the image where the information changes in every direction, versus an edge is only changing one direction. So, because this is geographical data, what it means is that there is a geographical characteristic like a lake or a mountain, and that information will affect the inhabitable area. I use the Harris corner detection, and this provides a small improvement. It's the only one in the chapter. One of the interesting things about the corner detector is that it has a number of parameters that need to be set by hand, and the recommended way is to do it graphically. So I plot a number of variations using different parameters for the detector, and I just look at which one seems to be more informative, and I pick one. Interestingly, this is the number of corners detected, and this is the logarithm of the population. So what we get here is that extremely flat places don't tend to get that big. Yeah, it's like it's just too uninteresting. People don't. The other number of corners are all over the place, but then if you have a lot of corners, then you have this gap here in the middle. And that gives you the idea that, okay, you have some places that are quite mountain or windy, etc., and they are still very big, but they are really exceptions. But after a certain stage, cities cannot grow that big if the terrain is incompatible. And this is something I will be interested in talking with somebody in geography, because it may be an interesting thing to analyze. And then the last technique I looked was into histogram of oriented gradients, where you compute a table of counts for each different segment about the different direction of growth of the system. And this didn't work either. So the interesting thing, as I was mentioning, is that I asked my friend who is a computer vision expert, and he said, well, the vectors is the beginning of a larger set of techniques, call it texture features, and there is these local binary patterns or LBPs that really show that will make sense for this data set. But one of the main things he stressed is that in this data set, the absolute position is not important. But there are a lot of problems that people tackle in computer vision, like face recognition, where the absolute position is important. So, you have one eye here and the other eye is here, it's not here. So the absolute position is meaningful and carries meaning. But to be able to make the absolute position carrying meaning, you need alignment. You need all your training data to have the same meaning, but this data set doesn't have any alignment. The center of a city doesn't really have much meaning, and you cannot really reorient each of your cities to be aligned. So it cannot be built automatically either. So from his expertise beforehand, he will have known that the pixels of features were not going to work. And in the same way, the histogram for gradients was not going to work, etc., etc. So back to the importance of domain expertise in data science and feature engineering, what I felt is this Spanish proverb that says, el que no tiene cabeza tiene pies, which means if you don't have a head, you have to have feet. Yes, if you cannot take a very smart decision, you will have to take a very laborious one. And also, I remember a talk I have with friends in IBM about how in computer vision, just coming up with features is way more laborious than in natural language processing. So one of the papers we look at the data science reading group last June is called Many Analysts, One Data Set. It's from 2018 by a number of psychologists. They took 29 teams involving 61 analysts and used the same data and asked them the same research question, whether soccer referees are more likely to give red cards to dark skin tone players than to light skin tone players. So you have the same data, a reasonable research question, and 29 teams of people. You will expect that everybody will come up with the same answer, right? It's the same data and the methods. Nope. 70% found it was statistically significant, 30% found it was not. And a big part is, sadly, many things we take in data analysis as rock solid truth end up being quite subjective. And I do find that quite, we need much more studies of this type. I would like to think that this issue of the domain expertise will be quite interesting to also look into this type of studies. So to conclude, feature engineering is a way of adding human knowledge and intuitions to a machine learning solution. There are a number of well understood methods and transformations. The process is better done iteratively, starting from exploratory data analysis and doing error analysis for each iteration. It's, you can do purely data-driven techniques and get you close, but if you type into domain expert, you can go faster and achieve better results. And investigating the impact of domain expertise beyond the anecdotal, I believe it can be a formidable research contribution in the field. I have also 2 invitations. I'm giving a talk next week at the Data Science for Social Group meetup downtown on Siamese neural nets for curriculum alignment. This was a hackathon I was invited in Google San Francisco a month ago. And then this Learn Data Science reading group that actually meets at the SFU Harbor Center. It happens every 2 weeks, and next week we are going to see a paper about data set drift and certainty estimation. Thank you very much. Questions, comments?